Hey guys, Pankaj here. Welcome back. Today in the statistics, we are going to see what is histogram, what is PDF, that is probability density function, what is CDF, that is cumulative density function, and what is KD, that is kernel density estimation. Okay, and we'll see what is the application or what is the reason behind using PDF and CDF. Okay, so let me share my desktop. Okay, so these are the topic which I'm going to cover. So as usual, we will be importing all the necessary libraries, the NumPy, Pandas, Matplotlib, SPyPlot, PLT, and Seaborn as SNS. Okay, so first we'll see histogram. So let me explain what is histogram first. So I've already shown how to plot them, right, in Seaborn as well as Matplotlib, right? So let's see what is the concept behind plotting the histogram. So let's say you have some data here. Why it is not working? Okay, so here let me just use this color. So assume that you have one data which is having some number, let's say 10, 20, 30, 10, 20, 40, 10, and 50. Just assume, okay, some data is there. So here basically in histogram, right, what exactly we do basically, we take the count of or frequency of, how it is defined basically, frequency of a number in a given data set. When I say frequency means how frequently it is going to come and how many time it has come in the data set. Okay, so let's say 10, how many time it has come? 1, 2, 3, right? So just write 3 here. And now let's say we have 20. So we have 1, 2, it came 2 times. Now we have 30. So 30 has come exactly 1 time. Then we have 40. 40 has come exactly 1 time. And 50 has come exactly 1 time. Okay, so now once you got the frequency right, I mean the number which is occurring how many times in the data set, you are just going to plot them. Okay, so let's say I'll just 10 here, then 20, then 30, then 40, and then 50. And here this is your x-axis, that is your element number, and this y-axis will be your basically count of those numbers. So 10 has come how many times? It's a 3 times. So let's say here we have 1, here we have 2, here we have 3, 4. Okay, so 10 has come 3 times. So let's plot 10 here, one vertical axis. Okay, then 20 has come exactly 2 times. So just plot here 2, and 30 has come exactly 1 time, 40 also 1 time. Okay, and 50 has come exactly 1 time. So what it is telling, this is what is your histogram basically. Okay, so 10 is coming 3 times, so exactly at 3 it is plotted here. 20 is coming 2 times, exactly at 2 it will be showing this point, and 30, 40, and 50 at 1 time. So this is what is your frequency plot. So in histogram, what they do, they basically take the bin size. So bin size is nothing but how many buckets. Okay, so in the bucket, let's say I give a bucket of 10, between 10 to 20, how many numbers are there? So that will be a 1 bucket. So let's say I give 1 bucket here. Okay, this will tell how many numbers are there between 10 to 20. Okay, and this is there is another bucket where I'll mention 20 to 30. This is another bucket where 30 to 40. This is another bucket 40 to 50. Okay, so like that. So if you are going to put this count in this bucket, right, so 10 to 20, how many numbers are there? We have 3 plus 2, 5, including 20 also. Okay, so this you will put 5 here, and between 20 to 30 you have 2 plus 1, that is 3, and 30 to 40 we have 1 and 1, that is your 2, and between 40 to 50 how many members are there? 2 numbers, so that is 2. Okay, so once you plot in histogram, right, it will be exactly shown like this. So between 10 to 20 we have 5 numbers, right? So exactly it will be shown as 5. So there will be one rectangle plotted here. Okay, now between 20 to 30 how many members are there, or how many numbers are there? 3. So let's say we have 1, we have 2, we have 3, we have 4. Okay, so between 20 to 30, so let's plot here 30, 40 and 50. So 20 to 30 we have three numbers, so just go ahead and take this 3, and this is your range for 20 to 30. This range is your 10 to 20. Similarly, we have 30 to 40, how many numbers? 2. So just plot like this. 40 to 50, another 2 numbers, right? Just plot like this. This is what is your hist. That is nothing but histogram. Okay, so this is what is histogram. That is nothing but a frequency plot. How many number of time that element has occurred in the data. Okay, so either you plot, this is known as basically stem plot, but this is also kind of count, right? They are showing the count. So best way to visualize histogram is basically this blocks. Okay, so let's go ahead and just plot it. So we should have some data to plot it, right? So what I'll do, as usual, I'll just take one data frame from Seaborn, load data set, and famous data or toy data set is nothing but iris, right? So let's use that and plot them. Okay, so in this data set we have this is basically a category of flower where 3 categories are there: setosa, virginica, and versicolor. Okay, and each flower is having different sepal length, sepal width, petal length, and petal width. That's what is this data all about. So now let's say I'm going to plot histogram of petal length. Okay, so how you can plot that? Basically, SNS dot, we have hist plot df dot petal length. So what is happening basically here? It is going to take all the data between 1 and 1.5. Okay, so if you see here, we have, let me just draw it. So 1 to 2, we have, let's say 1.5 also, right? Between 2 to 3, nothing is there. 3 to 4, so this will be 3.5. Okay, 4, and let's say this is 4.7, 5. So basically bins are created. Okay, so by default, his plot will take bin size as 10. So let me just show here. If you see here, bins are auto, so we can set the 10 also. So I'll just show the variation, how you can change the bin size. Okay, so basically bins are nothing but, as I mentioned, right, 10 to 21 bucket is there, that is your bin size. 20 to 30, that is another bin size. So if you want to increase the bin size, you may have to break the distribution in a more smaller size or more granular way. Okay, so earlier we had one bin between 10 to 20, right? So I want to increase more bins, so what you can do? 10 to 5, 5 to, sorry, 10 to 15, 15 to 20. So between 1 we have divided into 2, right? So that's how you increase the bin size. So more the bin size, then more granular data will be plotted. Higher the bin size means a lot of data will come into one bin. Okay, so let's go ahead with this plot then. Now I'm going to increase bins as, let's say, right now how many bins are there? 1, 2, 3, 4, 7, right? Let's say I create bin size as 5. You see the difference here. So 1, 2, 3, 4, 5, 5 bins. So between 1 to 2.2, let's say, then 2.2 to, let's say, 3.3, between 3.3 to, let's say, 4.5, like that it has created. Okay, so under that, so let's say between 1 and 2.2, how many such numbers are coming? So that is what is the y-axis, so total count. So basically 50 numbers are there which falls between 1 and 2.2. Okay, similarly in between 2.2 to 3.3, how many such numbers are there? Maybe close to 3 or 4 numbers. Okay, between 3.3 to, let's say, 4.5, how many numbers are there? Close to 35. Okay, so that's how you plot the histogram. Okay, so yeah, so you can take another features also. Let's say you can take sepal length and sepal width and petal width also, and you can just plot it. Okay, so this is about histogram. Now let's see probability density function, what exactly it is. Okay, so this probability is nothing but, so let's say if you talk about histogram, right? Let's say if I talk about this 4, right? So how many times this 4 is coming? Okay, so if you go to the middle of this particular block, 4 is coming exactly close to 35. Okay, so this graph will tell exactly the count, but if I talk about what is the probability of petal length having size equal to 4, how many times it is coming? What is the probability basically? Okay, so when you start plotting the probability of that particular number, that comes under probability density function. So you need to calculate the probability of each number. Okay, so let's say 4, how many times it is coming? 35. So 35 divided by total number of occurrences. That will give the probability of that particular petal length. Okay, so if you keep plotting for each data point, it will create a probability of all the data points, exactly what is the probability of coming into the whole data. Okay, so how to get that? Let's get that PDF first. So we'll do some calculation here. So let's say we have petal length, right? So we have one function called np dot histogram. Okay, so this is going to return me the total number of count and each bin size. Okay, so I'll take same example here, petal length, and if you run it, it is going to return me 2 array. So what is the count of 1? That is what exactly shown here, right? 37, and since couple of more points are there, so it is added together and summing up to 50. But if you count them, it will be exactly 50 here. Add them together, it will be 50, because this point is included, right, in that bin. Okay, so this first array is nothing but to count. So I'm going to make count, and the next one is bin size equal to this. So print count, print bin size. Okay, that's what we got. So now if I talk about 1, what is the probability of getting one petal length size as 1? Okay, so what it is going to do, it is going to add all the bin sizes. Okay, sorry, it is going to add all the counts and use that as a divisor. Okay, so 37 divided by total count. Okay, so that will be probability of getting 1. Okay, so how we can do that? Let's say I calculate PDF, that is nothing but probability density function. Since it is numpy array, so I can iterate over each element, right? So I'll just use count and divide by sum of count. Okay, and this is your PDF. Okay, now let's go ahead and plot it. So what I'll do, SNS dot, let's say line plot, plt dot plot, let's say PDF. I hope it will work. Yeah. So this is the probability plot for the given number. Okay. So now if I talk about this, so let me increase the x ticks. Range between, what is the min? Let's say up to 10 I'll give. Okay, because by default it would have taken 10 bin size, right? Okay, so here it will show me the probability. So what is the probability of getting petal length as 1? So let me just use pen here. So let's say, what is the probability of getting petal length as 1? Okay, where like petal length whose size is 1. So this is coming under what? It is getting close to 0.0 maybe 7. Okay, so what is the probability? Basically 70% probability is there, like number petal length, where number length of petal is equal to 1. Okay, so let's say if I talk about this point, what is the probability of getting petal length whose length is 6? So you just plot about this and you just do the x-axis plot here. So it is going to come around 0.19. That is 19% probability of getting petal length whose length will be 6. That is what this PDF tells. Okay, but PDF doesn't tell how many such points are there whose probability is 19%. Okay, how many such numbers, or how many what to say? So this we got 6, right? So yeah, what is the percentage or probability of getting petal length 6 or below that? That number it doesn't tell, right? So to get that number also, it comes under cumulative density function. So let me plot that and I'll show you. Okay, so if you want to do PDF plotting here, so what I can do now, I'll just go ahead and plot PDF together. Okay, so Let me see if this works. No, it will be overlapped. I think this should be fine. So later we'll do a KD plot and all, then it will be easy to understand. So you guys understood this PDF, right? So you just pause it and understand once again how I am calculating it. So basically you are getting the count. So to get the probability of getting one whose length, petal length whose length is one, just get the total count total count of one and divide by summation of all the points. That will be showing the probability. Okay, but the problem with PDF is it is not going to tell how many such what is the total probability of getting, or total number of points getting petal length of having length as 6. So what is the total probability, right? That we will see under cumulative density function. So basically what it is, it will just, let's say you are going to calculate, let me take another color. So I want to find out what is the total probability of getting petal length whose length is 6, okay, out of the given data set. So you just plot here, okay, and whatever probabilities are listed here, right, that you sum together. And if you sum together, this plot is going to come something like this. Okay, so let me use another color once again. So when you get the total or cumulative probability, right, finding petal length whose length is 6, you are going to add all the PDF here, all the probabilities below this particular curve. So area under curve below CDF is nothing but your cumulative PDF. Okay, and that is what is called CDF, cumulative density function. So let's see how we can calculate. So to get CDF, what we can do, we already got it, right? So let me just check. So we are getting this. Now we will do something called, where is the PDF? I'm going to take PDF once again. So PDF, and if you take the cumulative, right? So we have something called CDF. I'll take one variable called cumulative density function, np dot cumulative sum, that is cum sum of PDF. Okay, and it is going to return me CDF. What is the probability? Now, if you are going to plot this, right, then it will make sense. So let me just plot plt dot plot PDF, plt dot plot CDF. Okay, so this is what I was talking. So this is the total probability. Let me just use pen again. Yeah. So to get petal length of 6, what is the total probability here? So under this, whatever you got, right, all the PDFs, right from point 0 or length 0 to till 6, you just add them together and this will be your final probability. Okay, so total 80% probability is there to get petal length of 6 for which particular species. So we have 3 species, right? So you can just calculate for different species. Okay, so let's go ahead and calculate for different species. So here, what I'm going to do now, I'm going to plot same, but this time df petal length, where df dot species equal to, let's say, setosa. Okay, equal to. Now do the same thing again to do this plotting. So I'll take this. Earlier I was taken as a whole data, right? Now I'm taking only that data wherever species equal to species. Sorry, setosa. Okay, so this is this. Now let's run and go at this. Yeah, this makes more sense. So let's take the pen again and understand this concept. So this particular blue line, right, this is nothing but your PDF, probability density function. What is the probability of getting petal length whose length is 2? So this comes around 1%. Sorry, 0.1. That is nothing but 10%. Okay, 10% probability is there whose petal length is equal to 2. Let's say you talk about 4. What is the probability of getting petal length whose length is equal to 4? It is coming around 0.21, let's say. So 21%. Okay. Similarly, if you talk about, let's say 6, what is the probability for getting petal length whose length equal to 6? So this comes around, let's say 0.18, almost 18% flower belongs to Setosa category whose petal length equal to 6. Okay, but this PDF is not telling what is the total probability for getting petal length equal to 6. So let's say I'm going to find the total probability of getting length equal to 6. So let's go ahead and plot vertical line on 6 and just plot this. Okay, so this is coming around maybe 85. So 85% of data or the element whatever we have got here shows that probability of getting petal length which is equal to 6 is having 85% probability. Okay. Similarly, if you talk about, let's say here we have 9, right? So 9 is nothing but that is the maximum length, right? So maximum length, of course, all the probability will be added together up to 9, and their chances will be exactly 100%. Means all the data which falls below or equal to 9 petal length is having 100% chance. Of course, because you have considered the whole data, right? In out of whole data, let's say, what is the probability of 4, getting 4, less than 4, right? So total probability will be coming around this. So this will be close to 41%. 41% probability of getting data whose petal length equal to 0 to 4, less than or equal to 4. So here for 6, less than or equal to 6, total probability is nothing but 85%. Similarly for 9, it is 100%. Okay, so that is what your CDF is. So cumulative density function. You get all PDF, do cumulative sum and just plot it. So this have very good example or very good application in the data set. So whenever you have PDF, CDF, right, or you have very large data set, so understand how many such data points are there whose probability is this and it is falling less than or equal to below that particular data point. Okay, then you go with PDF and CDF plot. Okay, so let me plot something else, then it will give much more insight about uses of CDF and PDF. Okay, so what I'll do now, let's say we have SNS dot disk plot df dot petal length. Okay, now here I'll use u parameter equal to df dot cs. Is not there. Okay, u must be there. Okay, I have to give x and y, right? Okay, so x equal to your petal length and u will be df dot species. Then I'll do little more modification, kind equal to, let's say, kd. Okay, and I'll make rug equal to true. It is going to show me more data points below that. Okay, so what this particular plot does, basically it is doing exactly same whatever we have done. So this is nothing but all your PDF, right? Under KD you see, right, these are probability density function, probability density plot. So here I have given petal length as data set and I have plotted for all kind of species. For Setosa we already saw separately, right? So this is what is coming here. Okay, let me see if we have cumulative. It's not there. Okay, that should be fine. So what exactly it is going to tell when you do this kind of plotting? So if you see here, right, for Setosa, the peak is here, right? It means more number of data points falls between, let's say, 1.4. So probability of getting petal length equal to 1.4 is higher than other points. Okay, that's why you see this is nothing but 80% probability to get the petal length between a petal length equal to 1.4. Okay, what is the probability of getting petal length? Let's say 4. So definitely this 4 is coming here. So this probability will be 20%. Okay. And here what exactly it tells? This orange color is nothing but for versicolor, right? So this belongs to versicolor. Whenever your petal length is less than, or maybe I would say petal length, if it is, maybe here it is coming as 2.5, right? If it is greater than 2.5 but less than 4, sorry, less than maybe 5.8. Okay, if it falls in this category, means your petal length belongs to versicolor species. Okay, similarly, if it is greater than, let's say PL is greater than 4 but less than, maybe I would say 7.5, if it comes, then this belongs to Virginica. Okay, so with the help of this kind of plot, right, you can easily create such kind of small model by just using this if else condition and predict, okay, or maybe decide this falls under which category, which particular flower category. Okay, that's what this kind of plot will tell. Okay, so that's about this PDF and CDF. Now let's go ahead and understand what is KD. Okay, one more thing I want to tell, if so this kind of probability, right, let me just go to whiteboard. So whenever you have plotted this PDF, right, if you are joining these centers for each bar, right, this is going to basically generate the KD plot. That's what is your KD plot. Okay, so KDE also tells basically smoothing the histogram. Remember that KD is nothing but, this basically tells smoothing the histogram plot. Okay, so there is a concept involved behind this. So whenever you have any kind of histogram, right, let's say I plot once again this, then we have another peak, we have another peak, and we have, let's say, this peak. Okay, and now you go ahead and mix, join all the peaks of these graphs, right? So whenever you are going to add them together, that is nothing but it is going to plot the KD for this particular plot. And that is what you may see in some of the graph, it is looking like this. That is your KD plot. Again, I'm reiterating, KD is nothing but smoothing the histogram. Okay, so let's see how it gets calculated. So application of PDF CDF I told, right? So once you plot this, you can easily understand basically how many such points are coming, which falls below that particular number. Okay, so PDF tells what is the probability and CDF tells what is your cumulative probability to get that particular numbers which falls below one to other number. Okay, so let's see kernel density estimation. So I'm going to plot those also. SNS dot KD plot TF dot petal length. Okay, so let me use another graph here. We have this plot, right? So under, as I mentioned, right, so to smooth the histogram, it is just going to join all the peak of each bar, right? And that will be taking a shape of KD plot. So here I'm just going to do as let's say kind equal to KD, that is kernel density estimation. Okay, and I wanted to show with hist plot. Dot hist plot dot petal length. Okay, here histogram as well as uh, KD is also there, right? Here, what I'll do, I'll just make rug equal to true. Okay, it's much better. So what exactly it is doing? As I mentioned, it is going to just join the peak of those, right? So somehow this peak is coming here, right? Because there's a concept involved behind that. So what it will do basically, how this KD being formed. So whenever you plot histogram, right, it will, as I mentioned, K stands for kernel, right? Kernel density estimation. So for each data point, right, whatever you see here, these rug is true when you make, then it is going to plot the data point. So when you see density more in this particular point, right? So that's why you are getting a bigger peak in this particular region. Similarly here, more density is here, right? You got bigger peak here. But how this peak is getting calculated? So what KD, basically how KD is working here, they are going to plot one small Gaussian curve for this particular data. Okay, for each data point, it is going to plot the Gaussian curve. For another data point also, it will just plot. For this plot also, it will plot, correct? For this particular data point also, it is going to plot. So at the end, what you're going to get, let me just explain in the whiteboard. Just clear it. Okay. So what exactly it does, let me create a bigger picture. So you have a lot of points here, right? So to make KD, it is going to take each sample, and for each sample, it is going to plot a small kernel here. That is small kernel is nothing but your Gaussian curve, right? So let me just mention this is Gaussian curve. So Gaussian curve basically got generated from normal distribution, Gaussian normal distribution. I'll talk about this little more when I talk about Gaussian curve. So basically, it has property means it will be looking at exactly as bell curve where your median equal to, sorry, mean equal to 0 and variance will be equal to 1. That is what is your normal distribution. So whenever any data point, if you say it is normal distributed, means it is following the bell curve where mean is equal to 0 and variance equal to 1. So that's what it is going to plot, this normal distribution curve or bell curve for each data point. Okay. Similarly, there will be some data point here. So many data points will be here and another data point here, right? So how this peak is getting calculated? For this particular point, how many kernels it is going to pass through? So there is one kernel here whose height is, let's say, this. There is another kernel whose height is this. There is another kernel whose height is this. Add all the heights, and that height is going to be coming somewhere here. Okay, and that's what you see the curve here. Okay, similarly here also, and somewhere, let's say you have a lot of data points here. So more the data point is bigger the height. Why? Because so many kernel it is going to pass through. And if you add each cross point of these kernel and sum together, that will added up to very peak, very bigger height or higher point, correct? And that is going to be your peak of that KD. Okay. Similarly, one peak is coming here means you are touching more small curve. So how many kernel it is passing through, add all the heights together and it is going to come here. Okay. And that is what is your KD dot kernel density estimation. That's how kernel is getting estimated. And this part we have already talked. Y-axis is nothing but your probability, correct? Okay, guys. So that's what I want to show here. So this is about PDF, CDF, and your histogram. I hope this part is clear because there's a lot of misconception about like all these curves are same. It is not same. It is having different mathematical calculation behind it, and that's how you get using this plot. Okay, so this part is very important. Again, I'll reiterate this PDF CDF together. PDF will tell the probability of getting that particular point whose length is this. Okay, but what is the total probability of overall data set? to get the petal length whose length is 4. So that's where your CDF will come into picture. And if you plot like this, you'll get to know 0.5 is the total probability, that is 50%. Okay. Now one more very important thing I wanted to show here. Let me see if I can get the plot. Yes, this is the plot I was about to talk. So let me see if I can take the screenshot, paste it here. Okay, it is not pasting. So what I will do, let me clear again. So whatever plot we did here, right, for Setosa, so it was like this. Okay, let me choose another color. And one plot was like this, and another plot was like this, right? Okay, so this is having, let's say, probability 0.1, 0.2, 0.3, 0.4, 0.5. Just for example, okay, just to mimic this particular data. So what is happening here, whenever you are developing a model just by looking at the graph, right? So you may give the, let's say, condition, let's say here it is 1, here it is 2, here it is 3, is 4, 5, 6, 7, 8, and 9. Okay, so this, by looking at this graph, it clearly tells if petal length is greater than 1 and less than equal to 2, means this is your Setosa. And let's say this is versicolor and this is your virginica. Okay, so this part is very much clear. It is pretty straightforward because the whole data point is falling between 1 and 2. Now what about this point? When petal length is, let's say, greater than 3 but less than, let's say, 6.5, it means your petal length belongs to versicolor category. Okay, up to here also it is fine. Now what about this data set? If petal length is, let's say, it is coming till here, greater than 5 and less than equal to 9, this falls to virginica. But now you remember one thing here, you notice one more thing, these particular points are overlapping between what? Versicolor and virginica. So what is going to happen? It is crossing somewhere here, let's say 0.18, right? 18%. So there is 18% probability that you may get the data which is falling between this triangle. Okay, what does it mean? Either it could be belonging to versicolor or it could be belonging to virginica. So what does it mean basically? 18% means total how much? 82% data you are very sure it is going to be versicolor for this particular category. I'm talking about only this. But out of 100%, 18% you are going to make error to declassify or wrongly classify the flower category between versicolor and virginica. Okay, because it is overlapping, your model will get confused whether it is falling in this versicolor or it is falling under virginica. Okay, so that's what, whenever you do this kind of plotting, right, it clearly tells there are chances of making error of 18%. So your model will not be accurate. It will provide accuracy of 82%, but 18% it is going to make a mistake by not classifying correctly. Either it could be versicolor or virginica. Okay, so 18% chances of error will be there in your model. Okay, so that is the use of this kind of graph. If you do PDF CDF plot also, you can see some cross or overlap, and using overlap you can clearly tell this many percentage. When you plot horizontal axis, whatever percentage is false, that could be taken as a chances of making error in that model. Okay, so that's what I wanted to show here. Okay guys, so I hope it is clear, and now you can easily understand what is histogram, PDF, CDF, how to calculate them, how to interpret KD, and how you can see whether your model is going to make some error or not. If it is going to make error, by what percentage it is going to make error. Okay, so that's all for today. Thank you so much. And I'm going to upload all those, let me just show here. I will be uploading all those notebooks as well as whatever necessary files are there, right? I am uploading under each video. Okay, so let's say if you talk about this statistics part 3, right? So let me remove this. So if you go here under show more, I have given these Jupyter Notebook. Okay, so you can have Jovian version as well as Google Drive as well as GitHub version. Okay, so click on that, download and run in your notebook also. And you don't have to write everything from scratch. Everything is written, you just use it. Okay, guys. So thank you so much. Have a nice day. Bye-bye.